screen now.
All right.
You can share your screen now.
Okay.
I want to welcome everyone to today's FANOG Functional Analysis and Optimization Research Group, FANOG, monthly seminar. This topic is titled Modeling with Fractional Differential Operators, Basic Idea, to be delivered by Dr. Andrew Omame. Dr. Andrew Omame is a young or highly productive expert in this area of research. Is well known both nationally and internationally, highly published author, and also among the top 500 authors in Nigeria. Is highly enterprising and an authority in this area. So we deemed it fit as a research group to invite him to give us this talk. We know that these days, interdisciplinary research is exactly what is selling, what publishes today. So for us in optimization, functional analysis, and other fields of mathematical sciences, it does make sense to understand his work in this direction. And I'm sure he's going to help us in all our various fields so that we can diversify our research. So without wasting much time, we've already spent much time already. So let me yield the ground to Dr. Andrew Omame, who is currently a postdoc fellow at the Abdul Salam School of Mathematical Science, Lahore. So Dr. Andrew, we thank you for honoring us and offering to deliver today's lecture. So the floor is now open for you to make your presentation.
All right, thank you very much. I hope the participants can hear me right.
Yes, as much as I can hear you, I think
yes, we can hear you.
Excellent, excellent. And again, just like in the memo, Prof said this seminar is in honor of our immediate past dean, Professor CCZ Akundisa, the dean of immediate past dean of School of Physical Science in Federal University of Technology. So personally, I am grateful to him for all his support, not just towards the research in Pluto, but personally towards me as a person. So I really want to, while I begin my talk, I want to also add my work.
So we appeal to all the participants, please kindly mute yourself so that we don't have any holdback at any end. So that it's only the presenter that will be allowed to have his speaker on so that we have a nice day. So thank you for understanding.
Thank you very much. So today we are going to talk about modeling with fractional differential operators. So I'm going to introduce basically some idea actually. There are some work which I've been doing here in Pakistan with my host. So which I feel I can be able to share the idea with us and we can build on it actually. So I don't know, maybe this talk may be like, because it's basic idea, so many of the things I'll be talking about today will be basic idea really. But then we're going to see how we can use fractional derivative, especially when we have problems involving fractional differential equation. How do we solve them? And somehow, I'm not going to say I'm going to be biased. Many of the discussions will be aligned towards partial differential equation problems. So from the PDE actually that we're going to look at, we can be able to recover the cases for the ordinary differential equation. More people are very familiar with the ordinary differential equation. So most of the things I'm going to discuss today, we can already recover the cases for And again, after the presentation, we are going to share the slides to the participants, so you can go through, do some practice on your own, and also ask questions as the case may be. So now, the highlight of the presentation as follows. We are going to have brief introduction of fractional calculus, some relevant methodologies, and solution of some problems involving fractional differential equations. Now, in applied mathematics and mathematical analysis in general, and any other field, fractional derivative is derivative of any arbitrary order. It can be real or complex. And the concept of fractional derivative was actually introduced by the famous mathematician Laplace in 1695, with letter to an orbital. And this new theory has turned out to be very attractive to mathematicians, as well as physicists, biologists, engineers, economists, and different areas of sciences. And in recent years, the fractional calculus draws increasing attention. Many people are beginning to gain interest, like what will happen if I consider a fractional form of this equation. You can see somebody has done something on classical integer derivative. You now say, okay, what will my problem or behavior of my solution look like if I consider the fractional scenario? And various types of fractional derivatives have actually been studied or introduced. We have the Riemann-Eagle fractional derivative, Caputo, Hadamard, Ederle, Koval, Grunwald, Letnikov, Machot, Real, and many others, many fractional derivatives. So fractional derivatives are usually defined via fractional integral. Most times when you see the definition of a fractional derivative, you see they'll give it in terms of fractional integral. There you have the kernel and the function involved under an integral sign. Now, before I continue, the real physical interpretation of fractional derivative in real life problem is still an open problem. So this is one point that needs to be clarified before we go far into all these things. But again, why fractional derivative has drawn attention is due to the curiosity of man. What happens? Just like Leibniz was asking L'Hopital, what happens if the order is not integer? What happens to the derivative when the order is integer? So now fractional derivatives have their advantages and disadvantages. Now, one of the points that we use in favor of fractional derivative is this memory function. And this memory function is defined in terms of the kernel. When you have the definition of the fractional derivative, you have the kernel. So in that kernel, you always see the memory term or the memory function, t minus t. So although this does not reflect any physical process, but again, when you go to the classical integer ordinary differential equation, you don't see this memory term. So this memory term is the ability of the fractional derivative to be able to capture what has really taken place in the past, the memory. And one of the great advantages, for instance, of the Caputo fractional derivative is that it allows the initial and boundary conditions to be included in the formulation of the problem. In addition, its derivative for a constant is zero, which makes it behave like towards the integer case. Now, the Caputo derivative is the most appropriate fractional operator to be used in modeling real-world problems. Again, recently there have been other definitions of fractional derivatives, such as the Atangana, Quagliano, Caputo, Fabio, and many others. So, and again, when Atangana was developing his fractional integral operator, he was trying to actually model these thermal problems in fluid mechanics. So his derivative was able to describe properly the fluid problem, which was actually trying to describe at that time. So this fractional derivative for some specific problems, you can actually say this derivative is better, this one is better than this one behaves well, and so on and so forth, depending on what you want to solve or answer at that time. Now, disadvantages, yes. Although there is this memory term in the fractional derivative, you can be able to incorporate initial boundary condition and so many other things in favor of the fractional derivative. There are still disadvantages. And the Riemann fractional derivative of the constant, for instance, is not zero. So when you take the Riemann fractional derivative of the constant, the expression is given by this equation. So in addition, if an arbitrary function is a constant, such as the exponential of the Taft-Leibler function, the fractional derivative at the origin has singularity. And these disadvantages reduce the applicability of the Riemann fractional derivative. So many people don't like using the Riemann fractional derivative. They prefer Caputo and other fractional derivatives. And now Caputo's derivative also demands higher conditions of regularity for differentiability. For instance, in order to compute the fractional derivative of the function in Caputo sense, you must first of all find the derivative. So for a function, whose derivative does not exist, that is the normal derivative, classical derivative does not exist, the capital fractional derivative may not be defined. And capital derivatives are defined only for differentiable functions, just like as I have explained. So for a function whose first order derivative might not exist, an alternative may be the Riemann-Leibniz fractional derivative, because in the definition of the Riemann derivative, even if the function is not differentiable, you can be able to find the derivative, the Riemann-Leibniz fractional derivative. Now, with the capital Fabrizio derivative, one of the limitations is that the kernel is local, and its derivative, when alpha is 0, does not give the initial function. Usually, when alpha is 0, you are supposed to recover the function. But for the case of capital Fabrizio, you do not recover the function. So this again is a limitation. So and many others. So some preliminaries. So let us consider a continuous function y is equal to f of t from our calculus, which many of us know. The derivative of the function is given by equation 2.1. So when you extend this to second order, you have the form given by 2.2. So many of us are aware of this. So again, when you go to the third order, so again, you have the form given by 2.3. So and by induction, you can be able to get the nth derivative of a function with respect to time for the integer case when n is an integer, or when n is not a fractional. So given by 2.4. Now, Grunwald in 1867 actually introduced the idea of representing fractional derivative as the limit of the sum given by equation 2.6. So provided this limit exists, Grunwald said if this limit exists, then this is the fractional derivative of the function f of t, where alpha, of course, is the order of the derivative. So using the identity given by 2.7, the expression in 2.6 can be written as the form given in 2.8. So now Leibniz gave this formula for the derivative of the product of two functions. When you want to take the fractional derivative of the product of two functions, you have the expression given under theorem 2.1. So I'm going to continue with introduction of some basic concepts. So this is the Laplace transform. So now, in order to be able to effectively solve problems involving fractional derivative, the knowledge, very good knowledge of Laplace transform is needed. So for that, we are going to have some basic idea of the Laplace transform. So the Laplace transform of the function is given by 2.9. So in this 2.9, for this 2.9 to exist, the function u r of t must be of exponential order. So it means that it must be bounded. When you multiply exponential alpha t minus alpha t with this, it must be bounded for all t greater than capital T. Now, the inverse Laplace transform is defined by the expression given in 2.10. So as I said earlier, this expression will be for a function of r and t, function of two variables. So again, when you have just f of t, you can easily write the expression for 2.9. So if you have f of t, the Laplace transform of the function f of t will just be exponential, the integral exponential minus st multiplied by f of t with t. Now, one important knowledge again that we need in fractional derivative is convolution of two functions. So the convolution of two functions is defined by the expression in 2.11. Why is the convolution important in fractional derivative? Because the Laplace transform of the convolution of two functions f and g is actually the product of their respective Laplace transform. So sometimes when you want to find the inverse of the product of two functions, this knowledge of convolution is highly necessary for you to do that. So again, there are other transforms also whose knowledge are highly needed or required in fractional derivative. So one of them again is the Fourier transform. So Fourier transform of the function u(r) of t satisfying certain conditions is defined by the expression in 2.13. And the inverse Fourier transform is given by 2.14. The Fourier transform of derivative, sometimes you can have an expression involving derivative. So if you want to apply the Fourier transform to derivative, the expression is given by the form given in 2.15. So if you have just the first derivative, then the Fourier transform n will be 1 on the right hand side. So if you have the Fourier transform of second derivative, partial squared, partial r squared, then the expression will be I omega, then product to the power of 2. It's the Laplace transform of u, and so on. So this is highly needed. So by the time we start solving some examples, you appreciate some of these definitions. So now, another knowledge which will really help us is the finite, what's called finite Fourier transform, Fourier sine transform. So what is the finite Fourier transform? So this is a kind of a special case of the finite Fourier transform, which already looked at. So finite Fourier transform for any function u of rt is actually given by the expression of 2.16. So and the inverse is a series given by 2.17. So now the finite Fourier cosine transform is given by 2.18. So later we'll see when am I going to apply finite Fourier sine, when am I going to apply finite Fourier cosine. So but these are just definitions for us to take note. So the inverse finite Fourier cosine transform is given by the expression in 2.19. And now this Fourier sine and cosine transform have some basic properties given by 2.20. Now these properties are very, very important. The finite Fourier sine transform of first derivative is given by the first expression there, minus bracket n pi over e. Then you see n of t is actually the finite Fourier cosine transform. So the finite Fourier sine transform is given in terms of finite Fourier cosine transform. So now for the